Hey you guys, it's Professor Brian Macon coming at you live. Well, I guess technically by the time you're watching this, it's not live, it's recorded, but anyway, you know what I'm saying. Coming at you live and in action. I want to show you how to do a quadratic regression or an exponential regression on Desmos, using the Desmos calculator here. Now, in a prior video that I created, we had an example of doing a linear regression, sometimes called a line of best fit, and didn't want that video to get too long, so I wanted to create a second video here showing you how to do some other types of regression. So again, typically when I want to do a regression, I'm going to click to add an item and choose a table, right? And that brings me here. And I'm going to enter my data in this table. So for example, let's suppose I have this data here. Right, so from a problem I'm looking at, I have some numerical data given to me. And you can see that the problem described here says the data in the table below represents the percentage of a country's population age 20 years or older whose age is X who do not have a high school diploma. So again, age A is my X variable, my independent variable, and then here's the percentage of students without a high school diploma. So the quote-unquote X value, right, my input is 20 and the output is 13.9 for that particular value. So I'm going to put in 20 and I'm going to put in 30.9, and there's my first ordered pair. And I would continue this process, right? My next order pair would be 30 and 11.5, so I would type that in as well. I don't want you to watch me have to do all of this, so let me pause for a second. Alright, so I've entered all my data here. You didn't have to watch me do that. And it's plotting my data. I just can't see the data in my viewing window here, right? So here's one of the things I love about Desmos is I can just use my scroll button, or I can use the zoom in and zoom out. Oops, I'm zooming in. I want to zoom out. And at some point, I should begin to see my data points, right? Here's my data points. Right. And something else just to point out to you, right? I could see my X's went from 20 to 70, so I could come over here, go to the window, and I could change, you know, from 20 to 70, my X min, my X max, something like that, right? And based on the outputs of my function, I could adjust my axis. There, I think the scrolling in and out is a quick way to view the data points, right? So this data is quadratic. We can see that sort of a quadratic function is going to fit this data set. So we're going to use a regression of a quadratic, right? So here's how we do that in Desmos. Right, my inputs are the x1 values, my outputs are the y1 values, and I'm going to put a generic quadratic equation. So I'm going to literally on my keyboard type y1, and then I'm going to use the tilde key to say approximately. There's my tilde key, and for me that was kind of the top left next to the number 1. And then I'm going to type ax squared because this is the standard equation for a quadratic. Right? So again, I'm going to use x1 because that's the label for my inputs. Right? I'm going to do say bx. Again, I'm going to type x1, and then I'm going to say plus c. Now, I just want to mention to you on my keyboard when I was typing X and 1, it automatically put the 1 as a subscript. I did not have to do that on my own. When I typed X1 here, again, the 1 automatically went as a subscript, right? And when I did the Y1, again, the Y automatically went as a subscript. So I just typed Y and then the number 1, and it fixed that for me. And you can see real quick here that the Desmos calculator is doing a regression, a curve of best fit, if you will, for those data points. And a couple pretty cool things it does for me here is it tells me what the coefficient of A, B, and C would be for this equation. So in other words, I would have like 0.03x squared, would have negative 0.27x, and then my C value would be 69.82. So those are the coefficients of the quadratic that fit this data point. And then it tells me the regression coefficient. Sometimes this is called the correlation coefficient. Probably in a class where you're learning about regression, you learn that the closer that this value is to 1, the better the fit is to the data. Right? How good of a fit do you want? I don't want to delve into that conversation. That's more of a statistics conversation. Right? That's another video I could create. But the closer this is to 1, the better the fit. And usually in some type of online homework system or some type of problem you might be working working on, they may ask for that correlation coefficient. So Desmos is providing that for us. And this is pretty cool too. I can plot the residuals. So here's what a residual is. A residual is like the error. So if I look at this particular point, the distance off of the equation is the error, right? So the equation is predicting the y value should be here, but the actual y value is here. So that's a kind of large error in comparison to this guy. You can see this point is closer. So the y value is being predicted to be here. The data point is a little higher. And we can see that this data point looks like it lies right on the equation. This one's really close to the equation, right? So the errors in these points are really tiny in relation to this one. And if I click to plot residuals, you can see those values, right? So basically, this residual is practically 0. I can see it's negative 0.1 units away. I can see this data point here has a residual of it's almost negative 5 points below. Just kind of cool. I can plot those residuals if I want. So there's an example of a quadratic regression. I'm going to pause the video real quick and we'll take a look at, say, an exponential regression. Okay, so pause the video so that you didn't have to see this in action. But here's a problem where we were given some data. We basically talked about the population of bacteria in a petri dish X hours after we began this experiment. So we put some petri dish into, we put some bacteria into a petri dish. We had an initial amount, it looks like, of 0.09 in my petri dish. Now, without getting too technical here, there's a couple different ways we can measure the population of the bacteria in the petri dish. One could be by weight. In this particular example, what's described is they utilize kind of an optical measurement. So we look at how much light can pass through the petri dish, and we can estimate the population in that manner as well. Without getting too technical, what we're looking at is some numerical data provided to us, and I have used the table entry, right? So I added a table and put that data here. Now initially it looks like this data looks to be linear, but as I zoom into this data, we can begin to see that it looks a little exponential here. Now you should know probably from some lesson in the material that you're learning that growth of populations behaves exponentially. So given the context of this problem, most likely the instructions are going to say find an exponential model that fits your data. So in that case, I'm going to come down here and I'm going to say that y1 is approximately, there's a couple of different ways to do this. We could assume that the exponential model's base e. So I'm going to put an arbitrary coefficient. I'm going to use the base of e, and I'm going to say raised to the power of b times x1. And again, I'm assuming there's a coefficient that I'm having the Desmos calculator determine for me, and then I'm assuming there's a coefficient of the domain input as well. And by making that assumption of form, we can see here's my regression line that's exponential in nature. We can see the correlation coefficient is really good actually. Here's the coefficient a, and then here's the coefficient of the exponential, here's the coefficient of the domain variable. Now, typically, like a TI calculator or other pieces of software use what they call the log mode of regression fitting, and you notice Desmos doesn't resort to that in default. Now, if you want to learn more about log mode, you could click the question mark here, and they explain it to you in a statistical manner. So if we choose log mode, you'll notice that these values change slightly, and our regression changes slightly as well, a correlation coefficient. So it's not defaulted, but typically that's the version that the calculator uses. Now, just want to point this out to you as well. We assumed a base E exponential model. Now, what if I don't want base E, right? What if I want the calculator to determine the best base, the better base, if you will, to fit this data? Now remember, E is approximately like 2.718. That's the base that we picked. This is a really good fit. If we plot the residuals, we can see, wow, those errors are really tiny, almost an error of 0 in those cases, all right? Now, if I wanted to, though, what I could do, let me come back here. Let me change this. Let's call this base the letter C. So I'm telling the calculator, find the best base for me. And notice that the base it chose was 2.02. So it's almost 2.718. Now, because I changed this base to let it find it for me, these values slightly change as well. And we should see the residuals be even better. Well, it looks like they're pretty close to the same. Here's typically what happens with Desmos. We only have a specific set of decimal accuracy, and the difficulty here sometimes can be getting more accuracy, and at the moment there's no way to change that accuracy. Alright, so that's how we would do an exponential regression. And then the concept is really the same. If I want aggression, man, I cannot speak today. It is Monday. I didn't have my coffee. If I wanted a regression that was cubic, which obviously would not fit this data, right? But I would do something like a x1 raised to the third plus b x1 squared plus c x1 to the first power plus d, right? And it would find a curve that fits that data, right? Now, I would see the regression equation in that case. Look at that. This is actually a really good fit. That's not supposed to be the case, but that's because I have really tiny data in that scenario, right? But I could change this model to be any form that I wanted. I could use a logarithmic model. We could do a sine model. We could do a sine of bx. Oops, I got to do x1. And it'll fit that curve, right? You can see here's that regression. So I really could pick any type of model that I want and just form the equation in that manner. All right, I hope this helps you with regression and Desmos. And for other resources, continue to check out my YouTube channel.